Welcome back, class. We have been looking at sound today. Sound as a type of a longitudinal wave. We've described what sound is, how sound is produced, and the different characteristics of sound. Now, let's look at thunder and lightning. Lightning is essentially light. It's a light wave. Thunder is sound. It's a sound wave. Whenever there's lightning, normally you can see it on the clouds. Then after a while, you hear the roar of the thunder. That's when most people are afraid. But the danger has already passed by that time. Lightning is much more dangerous, moving at 30 million meters per second, compared to thunder, which is about 300 and something meters per second. So here you have a diagram of a stormy cloud and lightning being produced from that because of the friction that occurs. Someone here is observing. This observer reaches the observer in 16 millionths of a second. That's very fast. The sound of thunder reaches the observer after about 15 seconds. 10 to 15 seconds later, the observer can now hear the thunder. That's because, like you say, lightning moves faster than sound. The observer is about 3 miles away. He sees the lightning on the flash 15 seconds before hearing thunder. And that means every 5-second difference equals to the distance of 1 mile. It's about 2.69, 2.7 kilometers. So that's how long is a mile is. So if we are to answer this mathematically, if we are to deal with this concept of the diagram here mathematically and try to verify this, we can have this example and we try to answer it. So the wave equation will come in handy because sound is still a wave. So a thunderclap is heard 12 seconds after lightning flash. Like I've told you, the sound is transmitted about 10-15 seconds after the lightning. A thunderclap is heard 12 seconds after a lightning flash. Calculate the distance to the flashing light. Take the speed of sound here to be about 340 meters per second. So, as it is with all numerical questions in physics, we have been given the time, 12 seconds. We have been given the speed with 340 meters per second. So, we're supposed to calculate the distance or the wavelength. So we know the wave formula. From the wave formula, F times lambda equals to V, and that means the lambda is V over F. So as it is with any numerical question, list what you have been given, identify the right formula to use, and then do substitution. V is 340. Okay, frequency is 1 over T. That means this one is Vt. So let's multiply that and see what we get. What do we have as a workout here? Speed is distance over time. So distance becomes speed times time. Okay, a much simpler way you can do it is that distance is speed times time. In this case, we have the speed and we have the time. So we do the multiplication. 340 meters per second multiplied by 12 seconds and gives us 4,080 meters. That means the distance here is about 4.08 kilometers. Sound waves on oscilloscope. Oscilloscope is a device that's supposed to interpret sound waves. Maybe most of the times from the heartbeat. Oscilloscope look like that. It's a device that is attached to patients to observe the heartbeat. When it becomes flat, it means that the patient has lost their lives. And that's what is normally displayed. The higher the wave, it means, or the higher the frequency, it means the heart is beating faster. And the higher the wave, the energy of beating is much higher in this case. You've probably seen this in movies or something, or in hospitals, you've been there, as monitors the heartbeat of a patient. Now this characteristic here, loudness, is a characteristic of sound. Loudness of a sound increases with the amplitude of the sound wave. In this case, the case of the sound wave, we have compression and their fractions, but can be formed on an oscilloscope as crests and troughs. So when the amplitude is high, it means this is a very loud sound. For example, the red wave here shows a quiet sound, but the blue one shows a loud sound because the amplitude is much larger than in the first case. So loudness is a property of sound which is denoted by the amplitude of sound on an oscilloscope. Pitch is another property of sound. The pitch is associated with music. In musical notes, it increases with frequency. The red wave here shows a sound with low pitch, musical note with low pitch. The blue one shows with high pitch because this one has like one wave, maybe half. This one has 1, 2, 3, 4. It's 4 times as much. So when you have the high frequency, it means you have more waves per unit time. That means that the pitch is high. For example, when you have a constant pitch A, it's about 440 hertz. When it is top C, it's about 523 hertz. These are musical frequencies. Doubling the frequencies increases the pitch by what we call octave. That's a musical sound, musical term. So therefore the frequency A above the top C will have a frequency of 880 hertz. So basically pitch refers to how high the frequency of sound in question is. Now, there's a question here. The diagram below on the opposite side shows an appearance of a sound wave or an oscilloscope. Draw a second diagram showing the appearance of a sound wave of a lower pitch but greater loudness. Lower pitch means that there will be less frequency. Greater loudness means there will be an increased amplitude. So how will that look like? Like that. Because the initial amplitude from the mid position was this much, this one is now increased to that much, so there's more loudness. But because the pitch is as low, you can have that as one wave, but here you have so many waves at the same point. So it has a lower pitch but greater loudness. How do you measure frequency? Using an oscilloscope, we take the time taken between the peaks of an oscillation. It should be equal to the period t. So the time taken from here to here, that's periodic time of that wave. Get that? And then we calculate the frequency, because frequency is supposed to be the reciprocal of periodic time. For example, if the t here is 0.05 seconds, you do your calculation, get the reciprocal, and the frequency should be 20 hertz. So that's how we get the frequency of a wave sound wave using the oscilloscope. We transform the sound into crests and troughs, get the time between two subsequent crests, and calculate it using the formula F equals to 1 over T. Another question is here. The distance between the peaks in the oscilloscope is 4 centimeters. If the oscilloscope time scale is set as 1 millisecond per centimeter, calculate the frequency of the sound. So you just calculate if 1 millisecond is per centimeter, what about 4 centimeters? It will be 0.004 seconds. Get the formula 1 over T, and you get your frequency here to be 250 hertz. So in summary, what have we learned in this lesson? We have understood what we mean by a sound. Transmission of a wave caused by, through a material medium caused by some kind of disturbance. We give the example of a clap, or the example of a meter rule hitting the desks. We have looked at related sounds. Sound, like all other waves, has some properties, and these properties are: it can be reflected, it can be refracted, it can be diffracted, it can interfere. And like all other waves, it has speed, v, it has frequency, and it has periodic time. We have looked at a few worked examples which give us this particular formula. We have seen that just like in the normal mathematics, distance is speed times time. This one is f times lambda, or this one is lambda over t. And you can work out different questions here. T should be that over that, and lambda should be vt, and so forth and so forth. So in our subsequent lesson, we're going to talk about how do you measure the speed of sound in air using two different methods, and how do you apply the fact that sound can undergo echo. How do you use that knowledge for practical purposes in normal life? And eventually, of course, you get the notes for this to write. So see you in the next lesson subsequently.